Here the question is, an increase in the value of the whole capacitor in the sample and hold circuit results in option A, decrease in acquisition time and decrease in drop rate. Option B, decrease in acquisition time and increase in the drop rate. Option C, increase in the acquisition time and increase in the drop rate. Option D, increase in the acquisition time and decrease in the drop rate. See, if we increase the whole capacitor value, the time constant is going to increase, which will increase the acquisition time as well as which will decrease the drop rate, means decrease the drop rate. That means option D is correct.
Now in this problem, we have to find the Taylor expansion of sin x at x is equals to pi by 6. Now, Taylor expansion in one dimensional, if f of x is any function at x is equals to a, is given by the formula f of x is equals to f of a plus f dash a into x minus a plus f double dash a by 2 factorial into x minus a whole square plus triple differentiation of f of a by 3 factorial into x minus a whole cube and so on. Somewhere nth term and so on again. Now here we have to find the Taylor expansion of sin x. So the value of f of x is sin x and we know the value of a, which is given as pi by 6. Now sin x will be equals to sin pi by 6 plus differentiation of sin at pi by 6 into x minus a, which is x minus pi by 6 plus double differentiation, that is d square by dx square into sin x at x is equals to pi by 6 into x minus a x minus pi by 6 whole square plus so on. If we simplify this expression, we'll get it as 1 by 2 plus root 3 by 2 into x minus pi by 6 minus 1 by 4 into x minus pi by 6 whole square plus so on, which is nothing but option 1. Now in this problem, I is given as integral over c cot of pi z by z minus I whole square, where c is the contour 4x square plus y square is equals to 2 in clockwise direction. Then we have to find the value of I. Now in order to find the value of I, so first what we do is we'll find the residue of the given function. Now residue of this function will be limit z tends to 1 d by dt of cos of cot of pi z, which is equals to minus pi by sin h square pi. Now from Cauchy's residue theorem, I is nothing but 2 pi I into residue. We know that residue is nothing but minus pi by sin h square pi, which will be equals to minus pi square 2i by sin h square x, which is nothing but option D. In this problem, we have to find the principal value of minus r power I. Now the given complex number is minus I power I. Now in order to simplify this, first we'll convert this minus I into mod ampere form, which says that e power I theta is nothing but cos theta plus I sin theta. Now if I take theta as minus pi by 2, then this will become e power minus I pi by 2, and cos of minus pi by 2 is 0 plus I into sin of minus pi by 2 is minus 1. So e power minus pi by 2 can be written as minus I. So I'll replace this minus I with e power minus pi by 2 in minus I power I, which is e power minus I pi by 2 whole power I will be equals to e power minus I square into pi by 2, which can be written as e power pi by 2, which is nothing but the principal value of the given complex number. That is option B.
Question is, Fermi level in p-type material is 0.1 electron volts above the valency band, whereas in n-type silicon material it is 0.1 electron volts below the conduction band. If the band gap of semiconductor materials, which is silicon, is 1.1 electron volt, then the barrier potential across the junction made using the above material is. Here we know from the Fermi level of a semiconductor material concept, this is the conduction band, which is energy band diagram. This is valency band. Here this is represented with EFN. The difference is 0.1 electron volt. Here this is EFP, which is the Fermi level in p-type material, which is 0.1 electron volts above the valency band. We know the difference between the conduction band and the valency band is the energy band gap, which is 1.1 electron volt in silicon. Now the difference between the Fermi level in n-type as well as the p-type is equals to E0, which is barrier potential. That means the barrier potential E0 equals to (1.1 electron volt minus 0.1 electron volt minus 0.1 electron volt equals to 0.9 electron volts, which is option C is correct. Question is, from the high frequency CV characteristics of a MOSFET given in the figure, we need to identify the which point indicates the accumulation condition. From the given diagram, the characteristics of a MOSFET are the p-type of MOSFET, because threshold voltage is negative. Hence, the characteristics are the p-type of MOSFET characteristics. For p-channel MOSFET, if for the p-channel MOSFET, if VGS is positive, electrons are going to be comes into the channel. Hence, that mode is accumulation mode. Here point T belongs to accumulation mode, which is option D is correct. Question is, the slope of the ID VDS load line for the circuit shown in the figure is. In order to find the slope of the ID VDS line, we need to apply the KVL in the output loop. That is, 8 equals to 1600 ID plus VDS plus 400 equals to 2000 ID plus VDS. And take the derivative of the equation 1 with respect to VDS. That is 0 2000 dID by dVGS plus 1 equals to dID by dVDS is the slope of the ID versus VDS load line. That is equals to minus 1 by 2000. This is option C is correct.